All right, gang. Now we are just at the end of the class today. If you're watching this on the video, we spent most of the class doing a reading quiz and talking about the quiz from yesterday. So, what's that?
Keep going.
Okay. So with just a few minutes left, I'd like to talk to you about some, one topic in the solubility chapter that will be different now. Remember that there is really nothing that's new in this chapter, and keep that in mind. I'm not teaching you anything new in this chapter. It's a different context of all equilibrium topics. So if we go to, and I don't think I erased what I had. Okay. I'm skipping over a couple of slides. Those slides I will come back to and do on Wednesday to kind of bring us all back here. But let's take a look at this. Now, knowing the little bit that we know so far about solubility, if you're asked to compare the solubility of two things, carbonates are typically not soluble and chromates are typically not soluble. So compare these two solubilities. Which one is more soluble? So you can look up the KSP values. KSP is SP stands for solubility product. It's just another expression for K in the specific case of solubility. Now the way we write an ice table, as I did over there for the reading quiz, we start with 0 of the products. We start with some amount of the solid, but it does not have a defined concentration because it's a solid. It's not dissolved in water. We can't talk about how much of it is present in the water because it's not really interacting with the water. It's a condensed form of matter. Aqueous and gases are not condensed forms of matter, so we talk about what their solubility is. However, for the change, this thing right here, and it doesn't look like a C anymore, for the change, that on the left side does matter. I'm going to call that minus X because as this reaction goes to the right and some of the nickel ions and carbonate ions break apart from each other, this amount is going down. And that part is being dissolved, and it does have a concentration. So as that goes down by X, these go up by X, like we're used to doing. And so at equilibrium, now, once again, what is the concentration of the solid at equilibrium? Even though it went down by some amount X, it still doesn't have a defined concentration. Where the nickel plus 2 has X and the carbonate has X. So the KSP, which is just the equilibrium constant, is going to be the nickel concentration times carbonate divided by, because that's a solid, 1, divided by 1. This whole chapter, I don't think we're going to have any denominators. It's kind of nice like that. So anyway, the KSP is just defined as X squared, which is 1.4 times 10 to the negative 7th. And take the square root, and you'll get X. And the question is, which is more soluble? So the question is, that thing right there, how much of that solid dissolves? That would be the square root of that number. Yes?
So from now on, we don't need to know solubility rules.
Oh yes, you still need to. For these kinds of problems, you'll be given a table of KSP values. Anything that has a KSP is not very soluble. So we're going to see a lot of hydroxides, because most hydroxides aren't very soluble. Carbonates, sulfides, those things aren't very soluble in this chapter. But you're not always going to have that table available to you, so you do have to know what things are soluble all the time. Like nitrates are soluble, sodium, potassium compounds, those always are. Okay, so making the ice table here, that's going to go down by some amount X, that goes up by X, that goes up by X. So that is going to be an undefined thing, but that's X. So the KSP for this thing is going to be X squared. And for barium chromate, the K value is 8.5 times 10 to the negative 11. I just call it 8. So when I take the square root of this number, that's going to tell me what the solubility is of barium chromate. When I take the square root of this value, it tells me what the solubility is for nickel carbonate. which one is going to turn out to be more soluble? So what I'm doing here is I'm taking the square root of that KSP and the square root of that KSP. Which one's going to be the higher value and therefore more soluble? This thing. Right. That one. Because the square root of this number, this is a bigger number than that. The square root of the bigger number is going to be bigger than the other. Than the square root of that. Okay? So this thing right here, this is our more soluble one. So you may generalize and say, hey, well, because this number was bigger, it's got to be more soluble. That's not always true. You can't just look at two values of KSP and say, okay, the one with the higher KSP value is going to be the more soluble one. It is true in this case, but it's not always. And let me show you why that is. With just 5 or so minutes left in the hour. Same question, which is more soluble, but now compare MnS, manganese sulfide, with that KSP value, to iron 2 hydroxide with that KSP value. What's going to be the difference with this problem compared to the last one?
2 to the OH is...
Yeah, this thing is going to give off 3 particles when it dissolves. That only gives off 2. That's going to make a difference. Let's take a look at this. Here are the chemical equations for the 2 reactions. And going through this is going to be a minus x, and plus x. So that at equilibrium, the K value, KSP, equals 2.3 times 10 to the negative 13th equals x squared. So just take the square root of that. That's going to give you that value right there. That's what is going to measure its solubility. Over here, because this is not 1-to-1 for everything, it's not going to look quite the same. When this goes down by x, the Fe goes up by x, but the hydroxide goes up by 2x. So that when we do the equilibrium line here, and the K, KSP equals 1.8 times 10 to the negative 15th. These numbers in this chapter, some of them are ridiculously small, like 10 to the negative 40th or whatever. It's crazy. And that's equal to what? This term, which is x, it's not a very nice x, times 2x. Quantity squared because of the coefficient there. So that number times that number squared gives us the K value. Now, what are we going to have to do to find x for this one?
Divide by 4.
Yeah, this winds up being 4x cubed. When you evaluate all that, it's 4x cubed. So you have to take that number, divide by 4, and then take the cube root to find x. Well, what would be the cube root of 10 to the negative 15th? Something like 10 to the negative 5th, right? So this is going to be around 10 to the negative 5th power, not points. I got a stray mark there. Ah! Where this K value, what's the square root of 2 times 10 to the negative 13th? Like 10 to the negative 7th or 6th, right? So let's even call it 10 to the negative 6th power. You can tell that this number is bigger. It's more soluble than this number is, even though it had a smaller KSP value. You see that? So when you're asked to find which one is more soluble, you don't just look at how big the K value is. You have to actually solve for the K value, or you can recognize, oh, this breaks up into 2 particles, I need to take the square root. Oh, this breaks up into 3 particles, I need to take the cube root. See that? And then compare the 2 K's from there. Don't just look at the raw K value. Look at what root you have to take of the K value to know which one is more soluble. With that, you can start the homework. You got 4 days off this weekend?
We have a 4-day weekend?
You can do a lot. You can do as many as you want to do.
This is going to be the best 4-day weekend ever.
No, do like the first section. The first section, until you get to the second topic. You can do that many.